Hello, Accelerated Chemistry students. This is Ms. Christopoli, and this is your Chapter 10, Section 2 video notes all over mole mass and mole volume relationships. Let's talk about the mole mass relationship. The molar mass of an element or a compound can be used to convert between the mass of a substance and the moles of a substance. The conversion factors for these calculations are based on the relationship molar mass equals 1 mole. So this is how we would represent them as a fraction. So let's look at an example problem. Let's convert moles to mass. So items made out of aluminum, such as aircraft parts and cookware, are resistant to corrosion because the aluminum reacts with the oxygen in the air to form a coating of aluminum oxide. This tough, resistant coating prevents any further corrosion. What is the mass in grams of 9.45 moles of aluminum oxide? Now, before we continue with this problem, I need you to make sure you have your calculator out, your periodic table out, and your notes, of course, because we always write sample problems down because we know that Ms. Christopoli is going to ask us problems very similar to this right after. So first, let's list the knowns and unknowns. So the mass of the compound is calculated from the known number of moles of the compound. So we need to go from moles to mass. Remember, in all of these problems, we're going to have to map out exactly what we need to do in order to convert from one unit to the next. So what do we know? We know the number of moles, and we don't know the mass. So first thing we need to do is we need to determine the molar mass of 1 mole of aluminum oxide. So we're going to write our formula down. We're going to take out our handy dandy periodic table. That formula has 2 aluminums in it, and each aluminum has a mass of 26.98 grams. We're going to look at the molar mass of oxygen. There's 3 of those, and that has each of them has a mass of 16. We're going to multiply, add that up, and you should get 101.96 grams per mole is the molar mass of aluminum oxide. Then we're going to identify the conversion factor relating moles of aluminum oxide to grams of aluminum oxide. And here's your relationship. 1 mole of aluminum oxide has 1.0196. That's the number that we just found on the slide before, the molar mass. And so we write this as 1.0196 grams per 1 mole. And we need to use that relationship. Like I said, 1 mole of aluminum oxide is equal to the molar mass of aluminum oxide. Now we're going to multiply the given number of moles by the conversion factor that we just determined. So we're starting off with 9.45 moles of aluminum oxide. We're going to multiply that by our conversion factor. Before we touch our calculator, we're going to make sure that our units cancel. They do. And so we're going to now type our calculator. 9.45 times 1.01.96. The number that we started off with, 9.45, has 3 significant figures in it. So our answer needs to have 3 significant figures in it. So 964 grams of aluminum oxide. So now what do we always have to do? We have to make sure that this answer makes sense because we can't just calculate things and not understand what we just calculated. So the number of moles of aluminum oxide is approximately 10, and each has a mass of approximately 100. So the answer should be close to 1,000, which it is. And the answer should be rounded to the correct number of significant figures, which in this case was 3, and it is. Let's look at another problem. Now let's go in the reverse. Let's go from mass to moles. So when iron is exposed to air, it corrodes to form a round rust color. Rust is iron 3 oxide. How many moles of iron 3 oxide are contained in 92.2 grams of pure iron 3 oxide? So again, let's list what we have and don't have. First thing we're going to do is we have to figure out our map. How are we going to get there? We're starting off with the number of moles we're starting off with the mass and we have to convert to moles. So we have to go from mass to moles. So what do we know? We know the mass of the iron 3 oxide and we want to know the moles of iron 3 oxide. So step 1. Since we're going from moles to mass, you're right. We need to determine the molar mass of 1 mole of iron 3 oxide, Fe2O3, 2 times the mass of iron, 3 times the mass of oxygen. Add them up, 159.70 grams per mole. When we write that in the conversion factor, this is the conversion factor that we get. 1 mole is 159.70 grams. And we're going to write it this way because we need to have grams on the bottom so that the denominator will cancel with what we're starting off with. And moles is what we want, and that is on top. So now we're going to multiply the mass given by the conversion factor. So here we go. 92.2 grams of iron 3 oxide. Here's our conversion factor. Grams cancel. Don't you dare touch that calculator. Make sure your units cancel because you'll be wasting time. Now you can touch your calculator because grams cancel and we're left with moles, which is what we're solving for. 92.2 has 3 significant figures, so our answer needs to have 3 significant figures, 0.578, and it does. Again, check. Does it make sense? It's about 1/2 a mole, and the answer should be about half. That's correct. Now let's talk about mole-volume relationships. The volume of 1 mole of different solids and liquid substances are not the same. The volume of 1 mole of gas, though, is more predictable because gases expand to fill their container, remember. So Avogadro had an hypothesis that stated that equal volumes of gases at the same temperature and pressure contain equal number of particles. So he's the one that came up with that particles that make up different gases are not the same size. However, particles in all gases are so far apart that a collection of relatively large particles does not require much more space than the same number of relatively small particles. Why is this true? This is true because when gases get into a container, they expand to fill that container. So, whether the particles are large or small, the space between the particles is going to be the same. So, when we're talking about the volume of a gas, it's going to vary with the change in temperature or change in pressure. Temperature is going to make the particles speed up faster. That's going to change the pressure. We're going to talk about all of that when we talk about gas laws in the future. The volume of a gas is usually measured at standard temperature and pressure. Standard temperature is 0 degrees Celsius, and the pressure is 101.3 kilopascals or 1 atmosphere. That is very crucial. Anytime you're not at standard temperature and pressure, you cannot use this conversion that we're going to derive right now. So, at STP, 1 mole or 6.022 times 10 to the 23rd representative particles of a gas, that's the key, this is a gas, has a volume of 22.4 liters. So the quantity 22.4 is called the molar volume of a gas. So then how do we use that? The molar volume is used to convert between the number of moles of a gas and the volume of a gas at STP. And we can use the conversion factors listed below, either 22.4 liters over 1 mole or 1 mole over 22.4 liters. So you can use these conversion factors to convert at STP. You can convert a known volume of a gas at STP to the number of moles of gas using the same conversion factor. So let's look at a problem. Sulfur dioxide is a gas produced by burning coal. It is an air pollutant and one of the causes of acid rain. Determine the volume in liters of 0.6 moles of SO2 at gas at STP. STP is the key here. So we know that it is a gas, and the volume at STP can be calculated from the known number of moles. So we're going from 0.6 moles. We know that 1 mole is 22.4 liters. And we don't know the volume. So we can identify the conversion factor. We're going to use 22.4 liters of SO2 as 1 mole from that relationship that all gases have a molar volume of 22.4 liters. We are going to multiply what we were given by the conversion factor. So 0.6 moles of SO2 times 22.4 liters over 1 mole. Moles cancel. Now you can touch your calculator. And that's 13 liters of SO2. Again, check your answer. 22.4 liters and 0.6 should have a volume slightly larger than 1/2 of a mole, or 11.2. So it does. It's 13 and half of a molar volume is 11.2. So you're good. And your answer should be to 2 significant figures, which it is. So now let's talk about molar mass and density. A gas-filled air balloon will either sink or float in the air depending on whether the density of the gas inside the balloon is greater or less than the density of the surrounding air. Gases have different densities, and the gas density is measured in grams per liter at a specific temperature. That is key. It's at a specific temperature. So the density of a gas at STP and the molar volume of a gas can be used to calculate the molar mass of a gas. The molar mass of a gas and the molar volume at STP can be used to calculate density. So let's look at an example problem. Let's calculate the molar mass of a gas at STP. What does STP stand for again? Standard temperature and pressure. So we have a gas containing carbon and oxygen, and it has a density of 1.964 grams per liter, and I want to know what the molar mass is. Well, what are the units for molar mass? The units for molar mass are going to help us here. The molar mass of a compound is calculated from the known density of the compound and the molar volume. So we know the density. We know that 1 mole of a gas at STP is 22.4 liters. We don't know the molar mass. Look at that unit for molar mass, grams per mole. That should help you out in how you need to set this up and what conversion factors you need to use. So we need to identify the conversion factor needed to convert density to molar mass, and that's 22.4 liters is in 1 mole. And that's because of this. Molar mass has a unit of grams per mole. If I take grams per liter, which is my density, times the molar volume, 22.4 liters in 1 mole, our liters will cancel and we'll be left with grams per mole, which is what we want. Units in this section drive the calculations you need to do. So you need to pay attention to your units in order to get these correct. So let's solve for our unknown. So I'm going to start off with what I was given, which is my density, multiply that by my molar volume, liters cancel, and I'm left with the units that I want, which is my molar mass, grams per mole. And since 1.964 has 4 sig figs, my answer needs to have 4 sig figs, and it does. And let's go over whether or not this makes sense. So since we had a calculated mass of 44 grams, about 44 grams, and the volume was 22.4, it's about twice as much, which is close to what the known density was. The density was like 1.9, and that's about twice as much. So that makes sense. And we need to have 4 significant figures in our answer because our density had 4 significant figures in our answer. All right. Finally, let's talk about the mole-volume relationship. So this is going to be on your mole map activity that you're going to be working on the rest of this week. And so this is kind of like your go-to. Mole is in the center, and you can use it to convert to any other part, representative particles, mass, or volume. And as always, all of the information on these Google Slides has been acquired and adapted from Pearson Chemistry's 2012 edition of the textbook resources CD and pearsonchem.com. Have a great night.